I'm talking to Professor Norman Billingham from Sussex University. Thanks for coming in, Norman.
My pleasure,
if I was
Jonathan.
to ask you what type of scientist you were, how would you reply?
But basically, I count as a chemist. I've spent my entire career looking at polymers, plastics as the general public knows them. Part of my time making them, a great deal of my time trying to understand how they degrade in the environment and how they disintegrate and how you can develop ways of stopping that. And in the very latter part of my career, trying to find ways of accelerating degradation because of all the problems that people perceive about disposal.
Yeah. And is that, I mean, it sounds like it's mainly experimental, but do you have theoretical work?
It is theoretical partly, but certainly predominantly experimental. I mean, I went into science because I enjoyed doing experiments, and so it's been very much an experimental field for me. We do develop theoretical models a bit, but nothing comparable with the real hardcore modelers.
I understand. And was there something when you were a child that really inspired you in science, that got you going? Is there any one thing you can remember?
Nothing very specific. I mean, I started out, at the very beginning, I didn't want to be a scientist. I wanted to be an engineer. I grew up, I was born and brought up in the Black Country, surrounded by what was then British engineering and huge numbers of factories that made bits and pieces for motor cars. And I had, both of my grandfathers were practical men, an iron founder and a shoemaker. So as a young child, I really wanted to follow in that sort of view. I wanted to make things on lathes and milling machines. My father, probably much smarter than I was at the time, realized that that wasn't going to be a long-term career. When I went to grammar school, I just discovered that chemistry was the one thing I could really do very well. I just fell into it and fell in love with it. And throughout grammar school, I was just very, very involved. Just nothing else I really wanted to do.
Could your dad see that the production of stuff was going to go down?
Oh, I think he was an accountant. He had no practical ability at all. But I think he realized that these industries were dying and competition was coming in from abroad, and that they were all going to decay away, which of course they have. If I go back to where I was born now, you would never know that it'd ever been an engineering area. The steelworks and all the factories and the mines that I used to crawl over as a small child have all gone completely. It's a totally different world now.
Yeah, so you talk about your interest in polymers, but actually we've got a clip here. I think I've got a picture here of a beautiful train, and you wanted to talk about this.
Well, this is really part of my retirement hobby, I guess. I mean, as I got into retirement, as I said, I've always been interested in making things. I've always had a workshop in the back garden and built models and built furniture and built all sorts of things. And I got involved with Westdean College, which is just down the road here in Chichester. And Westdean runs they run a great many short courses, weekend courses and week-long courses for amateurs, but they also have about 70 full-time postgraduate students in the background who are doing work, learning about conservation of all kinds of objects, clocks, metalwork, ceramics, books, paper, musical instruments, all sorts of stuff.
And there's a tremendous amount of chemistry in that.
Well, that's what's happening, of course. If you go into the museums these days, they're becoming more and more scientific. You know, there are now electron microscopes and infrared spectrometers and all sorts of kit in museums, and they have enormous problems with material degradation. You know, the art world has always been tremendously good at picking up new materials science and new materials. You know, it's usually the military are the first people to pick up new materials, and then the art world picks them up. And probably quite rightly, they have no real interest in their long-term stability. So we now have all sorts of things that were produced in the 1950s and 60s on the walls in museums deteriorating like mad, and a massive set of problems in understanding what's going on and how to conserve it. This particular thing, this is a model. It actually relates to another of my interests. I was at the time chairman of the Society of Model and Experimental Engineers, and we were given this model.
How big is this normal?
This is about 20 inches long.
Oh, okay.
It's a 5¼ inch gauge model of a locomotive called Jenny Lind, and Jenny Lind was the first sort of real locomotive that actually looks like a proper one that we'd recognized after things like rocket. And it was built, this one was built originally, the real thing was built in 1846 for the London Brighton South Coast Railway.
Oh, right.
And the man who donated it to us, his great-grandfather built that model in 1874, which means it would have been built pretty much by candlelight with a treadle lathe and a few files and cold chisels.
And it's a working model?
It would have been a working model, yeah. I mean, if you look at it closely, there's quite a lot of wear on the bearings and the cylinders, which suggest that it's actually run and hauled passengers It had been taken out to South Africa. It had spent a long time there in a garage. It had been painted a few times. Sorry, it had been polished a few times with the brass work with Brasso, which had been done extremely badly. So it was all over the residues were all over the thing. It came to us as a donation, and the big question was what to do with it. I mean, it's clearly a historic artifact of some.
When you say it came to you mean?
Well, it came to the society. It was donated to the society, and I said at the time I was chairman, and I looked at it and. In the state that it was in when it came to us, there was no way we could really. You can there you are. You can see what it was like. I mean, all these brass bits have been endlessly polished with Brasso, really rather badly.
So it isn't necessarily oxidation.
No,
it's
that's
just junk.
A lot of that is some of it is oxidation of the paint.
Yep.
A lot of it is just junk, and there was a lot of crackling of the paint and a lot of deterioration of the brass work, and various bits were coming away. So I kind of thought, well, here's a way of getting a number of interests together all in the same place. So I went to Westdean and talked to John Privet, who's the senior tutor in metal work, and said, firstly I said, what should we do with it? And he gave me some various suggestions. But then I said, well, perhaps you'd like to take it on as a student project.
That's a project, yeah.
So a couple of the graduate students in Westdean took it on under John's supervision. And I teach fairly regularly over at Westdean. I go over there and teach material science and chemistry to all the postgraduate students. So I was able to go along and watch what was being done and keep an eye on it. Yeah. Not just a simple job, because a lot of ethical discussion about what you're actually trying to do with a thing like this. You can't restore it to its original condition. That would be a massive intervention in the thing.
Do you think you might destroy, actually in the process of taking it apart and restoring it completely, you might damage it more? Is that what you mean?
I think partly you might damage it more, and partly you just take away the history of the thing. Yeah. It's the standard argument in all conservation. What are you trying to do? Are you trying to restore this to its original condition? If it were, if you bought an old sports car, you might feel that you wanted to take it to pieces completely, rebuild it and drive it around on the road. But if you've got something which has had a history, has had a life, has a patina, has deterioration all over it, you probably want to sort of try and stop the deterioration, bring it back to what it should look like.
But keep the sense of history.
But keep the sense of history that belongs with it. So it's a mixture of very practical stuff. What do you do? How do you do it? Ethical discussion, and a lot of science about what's it made of, what are the materials. You can see there what a beautiful job they made of it. It's nothing like the way it left the factory, so to speak, or left the model maker, but it's in good shape.
Do you have the problem that sometimes you just can't get the materials anymore?
Oh yes, absolutely.
So then you really can't replace it. You just have to try and do the best you can.
You have to try and do the best you can.
Yeah.
And of course there are situations where you simply can do nothing. I mean, in the early days of plastics, they made a lot of things out of cellulose nitrate, for example.
Yeah.
And cellulose nitrate was grabbed by all the artists a great many of the artists of the time. There were a whole bunch of people who made things out of nitrate plastic, and often incorporated metal. So you have copper in contact with nitrate plastic. Over a period of time, that stuff degrades. You can do nothing to stop it except put it in a refrigerator in nitrogen. It's just going to go. And so there are artworks now that were made in the late 30s which have just vanished. They come out of the museums take them out of store, and what they get is powdered plastic and green copper, and that's the end of it. I mean, there's nothing you can do except make another one.
And was that like a built-in obsolescence? There's nothing they could have done. They couldn't have made it better, or it's just
you could have made things better at the time if they'd understood it. But at the beginning, when plastics first came into being, they were looked at largely by people who'd been combustion engineers during the war, and they looked at all these hydrocarbons, plastics, polythene and polypropylene and all these things, and said, well, we know that these things don't start to oxidize till you get to 300 degrees or so. So clearly these plastics are going to have infinite lifetime. The reality is, what they didn't recognize for perfectly good reasons, is that impurities and defects in these things cause problems, and they depend for their properties on very, very high molecular weights. So a small amount of chain cleavage and the mechanical properties go.
And oxygen's pretty reactive, isn't it?
Oxygen is pretty reactive. We can't live without it, and we can't live with it. It's, if you start getting free radicals formed in a plastic matrix, they react with oxygen instantaneously.
So how much work was required to restore this to the level where you were happy?
Well, it took a year of 2 students' work. Now, that doesn't mean that they were at it 8 hours a day for the year. I mean, they did it a little bit at a time. It's work, the actual practicality is work that requires infinite amounts of patience. Every square millimetre of that was cleaned with Q-tips. And you have to do a lot of testing, first of all, to try and determine what the paints are, so that you don't go in there with a solvent
and just take it off.
Dissolve the paint.
Yeah.
No, you don't take the paint off. We left all the paint on.
Yeah.
But you want to make absolutely sure that you don't dissolve anything.
Yeah.
And then you've got to remove the dirt. And there are various techniques. I mean, you can do it with there are techniques involving laser ablation that will take off dirt without taking off the substrate if you're very careful.
Yeah.
But that was all done with solvents, very, very carefully. So a student would probably work on that for an hour or so, and then have a blinding headache and find it impossible to carry on. And so they would do. And then at the end, it's actually treated with microcrystalline wax to fill in some of the cracks and smooth off the surfaces and give it protection. And it now lives in the Society's headquarters in a specially designed case that we had made for it with silica gel in the bottom to keep it dry.
Yeah.
And hopefully it's got another good few years of life. But it's a nice example of how you can take, really rather fundamental science and apply it. And you see this across, as I say, the museums are full of plastics that are deteriorating and degrading, and we're trying to learn what they are. Think of colour photographs.
Yeah.
There's a huge archive of colour photographs, all of which are basically polymers, and they're all degrading in storage. And how much you worry about that depends upon what you think you want to keep. You can scan them and so on, but it's still, that's an expensive, long, slow business.
With all your experience, is there any kind of one principle or idea or technique that you found really helped you in your work?
Experimentally, the most important technique for all of this sort of stuff, and for a lot of what I've done, has always been infrared spectroscopy, because it's one of the few techniques that will really let you do quick, simple analyses of solid materials and solid structures. And of course, these days we have infrared microscopy, which allows us to look at very small detail in a thing like that. We can actually, you can actually take little tiny samples of paint and go through them layer by layer and figure out which material is which. Because one of the problems you get with polymers in these sorts of artifacts is that you've very rarely got one material. When you look in the literature, what we tend to do is to study the deterioration of polyethylene or polypropylene or whatever. In an artifact, what you've got is materials in contact with each other. So you've got metals in contact with paints, and metals are off. Something like that, the boiler will be made of brass. And brass is copper, and copper is a catalyst for oxidation of paint.
Right.
And so you have all sorts of
completely
issues
different issues.
You have completely different issues. And if you look in the bookbinding industry, you have medieval books which have got wooden boards with leather spine covers, and they're nailed on with iron tacks. And the iron attacks the leather, or the leather attacks the iron, and the iron attacks the oak of the book covers, and you just get an awful mess of deterioration.
It's a very complex system.
It's a very complex system. Ink in old books, you often find in old ledgers that if you look at the figures, the centres of the 8s and 0s have fallen out.
Right.
And that's because the excess iron in the ink degrades the cellulose underneath. So the paper itself is okay, but where the ink is, the paper degrades underneath it. And trying to understand that and stop it has been a very interesting bit of science.
Do you think, I don't know whether you can answer this, but whether a career in science is different from when you started now? Have you got any thoughts about that?
I think it's, certainly in chemistry, it's probably very much harder than when I started.
Oh, really?
Yeah.
Why?
Well, in some ways, okay, let's go back on that. In terms of actually doing chemistry, in many ways it's much, much easier now than it was when I started, because we now have computers. And so all our instrumentation is now vastly more reliable than it was. We don't spend hours trying to fix bits of kit that have gone wrong. They don't go wrong because computers won't let you do stupid things with them. Whereas the old-fashioned way where you twiddled knobs things could go wrong.
Well, you had to have such expertise to run the thing.
That's right. You had hordes of technicians around to run these, and you needed them. In other ways, of course, there isn't that great demand pull from industry that there was when I was young. I mean, when I started, when I graduated, people don't really believe it if you say these days that we used to sit around in common rooms discussing which company we might be prepared to go and work for.
Amazing,
there were all these big labs, ICI, BP, Esso, Shell, Dow, huge laboratories, all really trying to tame polymers, really. If you look at what they were doing, they were trying to take these new materials that had been developed in the 30s and 40s and make them work. The term plastic in the 50s and 60s was a synonym for poor quality material, because so often these things degraded, weren't very good. So you had this huge demand. There were big companies going around looking for people to employ. The average postgraduate chemist now is more likely to be working in a much smaller company, much more likely to be one of relatively few. So needing to be much more generally expert. When I graduated, move around more, do more things. When I started, you could be very specialized in industry. You could go into industry as a person who did catalysts or did oxygen absorption measurements or did NMR. Now you're like most of my graduate students who've gone into industry are very often one of 1, 2 or 3 polymer chemists. So they have to have a much broader base very early in their careers than I ever did.
Thank you very much for talking to me, Norman.
My pleasure, Jonathan.
Thank you.
Enjoyed it.